Hello and welcome. In this problem we have a rigid tank in which there is 1 kg of hydrogen and 5 kg of oxygen kept at 300 Kelvin. We also know the volume of the tank, so obviously we can figure out the pressure inside the tank. The mixture is then ignited and heat transfer occurs until the final temperature is 2500 Kelvin. Obviously after combustion probably the temperature is higher than that. We are asked to find the heat transfer using variable specific heat, that is IG model, but with equilibrium combustion. In other words, we don't know what the products are. We should allow all available species to be present in the final products. So first let us set up the fuel and oxidizer because the masses are given, and then we'll select the species for the products and then go about finding the equilibrium composition. So let's start a suitable test step here. So we go follow the closed system specific branch, and combustion and chemical equilibrium is covered in this node. And notice that the chemical equilibrium analysis is done only for pre-mixed. There is no non-premixed combustion here. So we click there and we end up in the very similar looking app. There are a few subtle differences though. So let's first go out and set up what the fuel is given in kilograms. So we got hydrogen is 1 kg, we add there, we're done with the fuel composition. Now we go to the oxidizer. We have been given there are 5 kg of oxygen. Once again I'm making a mistake. We must select kilogram and it's given to us. There we go. We click anywhere to turn it on to input mode, 5 kg, add. So we are done with fuel and oxidizer, as you can see. So we know there is so many kilomole of hydrogen and so many kilomole of oxygen in the reactants, and now it's time to deal with the products. For the products, we go there and we see a whole lot of species that you can make out of hydrogen and oxygen. Of course, there are more possible, but the database only provides these many, which are kind of sufficient. As a matter of fact, if you select typical products, when hydrogen and oxygen go to equilibrium at high temperature, those are the species that are mostly present. If it is hydrocarbon, you will find a whole lot more species in this panel. Of course, we can select and choose, or we can eliminate after getting an answer that is oxygen atom is really important. We can eliminate and resolve the problem. And that's the beauty of solving an equilibrium problem, that you can always refine your species in the products by knowing if it has any impact on the final answer, final outcome. Okay, so we are just selecting the typical products and adding them. So the reaction now is a little more advanced. We know exactly the fuel and oxidizer. This is our reactants, and we know what the products are made up of, but except we don't know their amount. And that's done by equilibrium analysis. So what we do now, we go to the state panel, and of course for the what is given is 300 Kelvin. The reactants are at 300 Kelvin, and 5 meter cube is the volume of the tank, I believe, and that should be completing the calculation of the reactant. So 325 kPa is the pressure of the reactant. Okay, state 1 was simple. How do we find state 2, the product state? We don't even know the composition. Well, we minimize the Gibbs function, and to do so we must know the pressure and temperature. Temperature is known, 2500 Kelvin, but the pressure we have no clue right now, except volume is known to be 5 meter cube. But notice if I give temperature and volume, we cannot find composition, because to minimize Gibbs function we need pressure and temperature. So we'll guess pressure, and that will produce a composition of the products, and that will produce a new volume, and we can iterate to find the correct pressure. So we'll start with a guess, assuming the products are the same as the reactant. If that were the case, using ideal gas equation, we can say, okay, then the pressure will be P1 times the ratio of temperature rise. 2500 is the current temperature, and T1 was the temperature at state 1. So now if we do a calculate, it produces the composition as you can see, but you can go back to state and check that the product's composition has been found here, and you say, oh, we found everything. No, not quite, because if you look at the volume, we did not get 5 meter cube. So to get 5 meter cube, we realize the pressure must be, right now, how much is the pressure? 2700. You can see the pressure appearing when you put your pointer over P2, it's 2711. So the pressure is a little bit too high. Let's reduce the pressure and redo the calculation. So what we do is that we say, okay, how about if the pressure is, say, 2000 kPa? That should increase our volume. Yes, it is more than 5. So if you iterate like that, we're quite lucky and have done a little bit of iteration, and I found that 2050 will produce pretty close to 5 meter cube of volume, 5.0. So that's close enough, let's say. So now that we have evaluated state 1 and 2 completely, we know the final pressure, we know the final composition, and these are the partial properties of each individual species of the products. And then we go to the process panel, and to find the heat transfer, that's pretty simple. State 1 and 2 are the beginning and final state. And of course, it's a constant volume process, but it's nevertheless good to put WB equals 0 because our volume slightly changed really. And that will produce the heat transfer in this case. So we have to have about 39.8 million joules of heat transfer loss from this to have final temperature of 2500 Kelvin. And of course, the final compositions are shown here as the final reaction that is completely given here. That is, with each species amount is shown here. A super calculate will produce a nice report, or super print rather. In the bottom, you'll find the reaction, the fuel, oxidizer products, as well as the properties of the states.